Thank you. So first, thank you for the nice invitation to present some results here. Um, I will entertain you about physics-informed neural networks, which are very nice and modern application of neural networks that has can both deal with physical constraints such as equations or conservation law, and also with data information. And there are many applications. I will not spend too much time on that. Um, what is the setting that we are considering here? So suppose we have some evolution equation, which is written here in equation one, like very simple state u, which depends on time, and there is some evolution operator g, which won't be made too precise. There can be boundary initial condition or not, and but what is the use of the neural network is to construct the solution simply. So if you have the neural network starting from a value of t and a value of the x or the vector x can be a vector, will construct the candidate of solution u of t and x, depending on the theta, which is our characteristics of neural networks, weights, biases, and so on, which are learnable. So this u of t of x should be the solution. Of course, this kind of approach leverages a capability of neural network packages to compute automatically derivatives. For instance, the time derivative, which is derivative with respect to the input. G can contain some spatial derivatives, for instance, for the heat equation. We will see an example later. And in any way, solving the equation means having this error term W equal to 0. So a good goal of the optimization part of the neural network is to minimize this norm of W square. And plus you can add terms which require that the initial condition should be the good one, and also the boundary condition. And you can also add some measurements if you have additional measurements or additional information, partial or total information. Just as a technical remarks, there are many derivatives here. This is one derivative. The stochastic optimization algorithm usually used will search for a second derivative. So here, for instance, the ReLU activation will not work because the second derivative is 0 almost everywhere. So there are some specifics of this situation, but I will not enter into that kind of details. So again, forgetting about initial boundary condition and other kind of additional data, suppose that we are concentrated only on the evolution equation. So we want to minimize this kind of loss functional norm of W, which is the error square. Of course, the solution is 0. Suppose that the neural network is expressive enough, which means that solution is a part of the reachable state for the neural networks. Solution is obtained when W is 0, which is the minimizer of this integral, and is also minimizer of this integral for any row of t which is positive. Okay, so we have some liberty here to choose the row which is the best one. Okay, so this is the main topic of this contribution, to look for which is the best sampling, time sampling here, that gives the best solution. Why I'm saying is a time sampling, because you see here is just like you multiply time by a weight. Having row taking large values means that you want to minimize this value of t with priority. So of course, when you compute, you have a computational budget, and you never obtain W equal exactly 0. So you will have it small, and the computational budget works like something like this. You have a upper bound of the number of computation you are allowed to make, and you can ensure that your W will satisfy that equation when you notice that having W equals 0 will give an infinite amount of computation, as it is classic. So the question is, given a B, which has a bound on this term, what is the best weighting scheme rows or density of time, which minimizes the final error? Or we can also minimize some other error which is accumulating over time. Okay, but I will mainly be concerned with the finite error here. Suppose that your goal is to compute the final solution and you want this to be as small as possible, knowing that you have a computational budget B here, and you cannot choose which W you obtain. You will obtain one which is compatible with relation 5, but you don't know which one. So you have a loss here. I'm just a reminder about the previous equations. Loss, which is depending on theta, which is the internal characteristic of the neural network, and also somehow depending on rho. Error here, W, is just the error of the equation. Well, an intuition that people already had is that, well, this is an evolution equation. So if you do some errors in the beginning, this will very badly behave because the error will accumulate in time, and you should prioritize solving with very high accuracy the initial moments of the time distribution, because otherwise you will diverge and there is useless to solve with high accuracy the later times because an initial one is already bad and will go all over the place. So this is what is called causal recommendation. So solve more precisely the initial points in time. So overemphasize the initial point at times, which means that rho should be large for t small and decrease later on in time. Question is this true? And what is the best one? Okay, so in general, a more philosophic question is this causal recommendation oversamples the past. Should we oversample the past information, the future one, or the present? Which is the most important has the largest contribution to the error? So, in fact, we are solving this kind of min-max problem, computational budget fixed. We know that this W will satisfy this equation, this inequality with B given or a constant, and the solution will satisfy that. We don't know which W will be chosen by the optimization procedure, and we want to, so in a very prudent approach, we suppose it is the worst one. So this is the exact solution. This is solution obtained by neural network. Suppose we obtain the one which is maximizing that. So how can I design a row which minimizes this error? There are other ways to formalize, and I refer you to some other papers. This can be solved and is interesting that it has a kind of nice solution. So for one particular situation, which is the simplest one. So the question is, well, at least for the simplest one, what is the prototypical answer? So for the simplest one, which is G is equal lambda U, lambda constant, which can be complex, then this error is optimal when W has a density which is exponential. You see that, well, it's not exactly lambda constant, but it's some very small modification of lambda, but is an exponential of the form exponential minus RT dt. This is the best sampling of time, which tells in particular that when lambda is negative, what is oversampled is the future, not the past. So I mean, we don't care about the initial errors, we care about the final errors. So why is so? Because it does not seem intuitive at all. This is so because when lambda is smaller than 0, we have a stable dynamics. It's just going to some equilibrium point. So in this case, you really don't care about the initial condition because anyway, the final solution will be the equilibrium. So all initial points will go to the same one. So you can make some error initially it is important to not make errors in the last steps of the time procedure. And there are three regimes. This one, the stable that I already described, the chaotic one, when the real part of lambda is strictly positive, and in this case is just kind of implosion. Any error this is the really causal intuition. Any error in the initial point will diverge exponentially to different final states and will behave bad unless you oversample the times. The initial times and take care to solve precisely the initial t moments. And there is a periodic one where it doesn't matter. You have to sample uniformly in time. And these are to be compared with other prescription in the literature, which are not exactly the same one. So some numerical results. We had just checked that we can find the real solution. We take just this toy example, which is of course not very realistic. We know precisely the solution in this case, but we just checked that our neural network is expressive enough. You see there to the left, I only put 500 epochs. Epochs here are very small. It's not the I mean, they are very fast numerically. And if I put more and I converge, and this happens, okay. So for the toy example, the question is, will the exponential parameter follow our theoretical prescription? So this is the most important picture in this case, which tells that, for instance, for lambda equals 0, which means it is an chaotic dynamic, is an explosive dynamics. The optimal lambda, optimal R, so optimal time sampling is an exponential with a positive R. I don't know if you see precisely, but the minimum here of the error corresponds to R equal precisely 2, or between 1 and 2, which means that this is positive. So in this case, you have to sample the initial points in time very fine to be sure that the error here is small. Let's go to stable dynamics, lambda -2. The minimum here is realized for R equal to -3. So again, the signs of lambda and R coincide, and we recover our intuition, our theoretical intuition. And for lambda equals 0, which is more or less a periodic, there is a plateau which contains the 0 point, meaning that there is no need to sample to have any priority in sampling between past and future. Burger's equations also give some interesting results in this case. So Burger equation starts here from a sine wave and arrives after some time to some kind of discontinuity. And in this case, we found also that while this is more or less consistent with the dynamics of this equation, which is resembles more to a periodic dynamics. What about the chaotic case? A chaotic case is the Lorentz system, for instance, with the Lorentz originals parameters, 10, 28, and 8/3. And these are the equations. This is a three-dimensional ODE. If you put no uniform sampling, so if you don't care about the time sampling, you obtain nothing. This is the solution, the first row mid plot. The solution is here, the true solution, and the numerical solution is the left column, which in fact, if you superpose them, you see it's almost 0 and has no useful information. They are completely different. So if you put no sampling at all, you obtain nothing. So in this case, you have to do some sampling. Otherwise, you don't obtain solution. So indeed, when you overemphasize the initial points, I mean, you put a distribution which is more concentrated on the initial points and penalizes more in initial error, you obtain good results, which are this one. R equal 10, sorry, and for R equal -10, which means that if you somehow you're wrong about the sign of the distribution, if you overemphasize the final points, then you obtain again no useful solution. So indeed, at least having the good regime of the evolution is important to obtain some solution. I will just conclude with some remarks of it is interesting that the exponential sampling, the optimal sampling, is of exponential type. This is the first order distribution, if you want, because any evolution has a first order, which is kind of lambda u. The question, there are some positive numerical results, and the optimal parameter is not explicit, optimal parameter being the R here that is given by the theorem. We don't know precisely in this case, you know, but in general, we don't know what is the dependence of R over J operator, but well, can be object of future work.